So right now I have my periodic table up. Ugh, sorry, down a little bit there. Okay, and if I was looking at the metallic characteristics of elements, so, and I wanted to figure out the trends of the periodic table. So the metallic characteristics of the periodic tables increase from left to right, or right to left, top to bottom, or bottom to top? Metallic characteristics.
Does it increase from left to right? And then top to bottom?
Okay, so you said from left to right?
Yeah.
Okay, and you said from top to bottom?
Yeah.
Okay, so help me. So we're talking about metallic. Where are the metals located at?
In the middle area.
Just in the middle area? That's where all the metals are located at?
The orange, the yellow, the lanthanoid, actinoids, transitional metals, and the post-transitional. So some of the blue, yeah.
Okay, so, sorry, get carried away. So these are all the metals.
Mm-hmm.
Okay, so where are the non-metals?
The bright green and the purple.
Okay, well, in terms of the periodic table, is that left or right?
Right.
On the right.
Right.
So.
Right.
You still found her? Are you still looking for her? Well, actually, I haven't found her yet, but Sprinkle is.
Okay, so was that Daisy that gave me those answers?
Yeah.
Yeah. Okay, Daisy. So if the metals are over here and the non-metals are over here, so wouldn't it make more sense for the arrow to be going from right to left? Is that what you said?
Right to left.
Right to left, right?
I said left to right, yeah. I might have wrote it wrong then because I wrote it on my periodic table, but I could have wrote it backwards. Okay, let me fix that on my table too.
Okay, so it becomes more and more metal-like as we go from left to right. I mean, from right to left. Sorry, I almost made that mistake again. Okay, so, and that makes sense if you think about it, right? So non-metals, metals. So we're going to be going in that direction. And so it's going to be more metallic as we go from right to left.
Mm-hmm.
Okay, and then it's also going to become more metallic as we go from top to bottom. So you're right on the top to bottom, Daisy.
I wrote that one right.
Okay. Good job. Okay, so let's talk about ionization energy.
So ionization does increase from left to right.
Okay.
And it decreases from top to bottom.
Okay, so you're saying it increases from left to right.
Yeah.
Okay.
Hopefully I wrote that one right.
Okay. Okay, so that's good so far. And you said it decreases from top to bottom. So we can say it increases from bottom to top, right?
Bottom to top.
Okay. Mm-hmm. So ionization energy is going to increase from bottom to top, and it's also going to increase from left to right. That's correct?
This is what happens.
Okay. So that's good. Let's see. What about radius, atomic radius?
Wouldn't it be the one that's the francium?
What about it?
Atomic radius, like the highest one?
So it would be the fattest, the biggest guy, right?
Yeah.
Not the
Mhm.
fattest guy, biggest guy. He'd be the biggest.
Yeah.
So you're telling me it's increasing from top to bottom,
Yeah.
okay? And then what about left to right? Which way is it? Or right to left?
I think
Right to left.
Smaller.
So it's increasing from right to left, or it gets smaller from left to right,
Left.
right?
Right.
yeah.
Okay. Pretty good. Simple. Okay. So there's one other thing. I think we talked about it. Electron affinity. The color. Let's use brown. Okay, so the electron affinity. So does the electron affinity increase? So electron affinity is the desire to get an electron. So, and it gets bigger the more desire you have to get an electron, the stronger you're going to be, stronger your electron affinity. Okay, so who's going to be who wants an electron really, 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 really bad?
The ones closest to the group 18.
Okay, so the ones that's closest to the noble gases. What are the group that's closest to the noble gases?
Halogens.
Halogens. Okay, so then, since we know that, are we going to increase? It's going to increase from left to right or right to left?
It's gonna increase from, it's gonna go to the right, left to right.
Left to right, okay. Okay, and then is it going to increase from top to bottom or bottom to top?
Mm, From,
From
I don't-
bottom to top?
Bottom to top, that is correct, Paz. Chlorine is going to be the one that wants it worse than anyone else, right?
okay.
Okay. Simple, right? You feeling pretty good? Feeling confident?
So far, so far.
So good, good. I like that. Okay, so let me clear. And then we'll get started with the lecture. So we're actually in chapter 12. If I can find it. So this is what happens when you have too many classes,
Mm.
too many lectures going on at once. Okay. So are you guys looking forward to spring break? Yeah, I would say I am too, but I'll just be I'll just have half the class or a little more than half the class. Okay, so let's
Yeah.
start off with ions. We've talked about ions before. Yes, no, maybe.
Briefly, I think.
So in the case of an ion, we've talked about a cation ion, right?
Yeah.
Okay, so a cation ion is what type of ion?
Positive.
That's right. It's
Positive.
positive. Remember? Positive.
Yeah.
I knew you had a joke in there, but I forgot what the joke was.
Cat. Pa.
Yes, I got it. Yeah, yeah.
Okay. Okay. So cations are positively charged ions. So the way that we get positively charged ions is by removing electrons. Okay. So the way things become positive or negative is going to be based upon either we're gaining electrons or we're losing electrons. So if we're losing electrons, the ion is going to be positive. If we're gaining electrons, the ion is going to be negative, or an anion. Make sense?
Mm-hmm.
Okay. So when we talk about, we've been working on Lewis dot structures, right?
Mm-hmm.
So if we look at our Lewis dot structure for nitrogen, how many valence electrons do we have for nitrogen? Let's see if I have my periodic table available. So we have nitrogen here. Here's
5.
nitrogen. So we have 5 valence electrons.
Mhm.
Okay, so how do I show that by using the Lewis dot structure?
You're gonna put five dots.
So I'm going to put 5 dots, right? Okay, how many valence electrons does, let's see, bromine have?
Bromine. I can't locate it. Let me see.
7.
7, that's right. Bromine is located right here.
Okay.
Okay, and so when we want to figure out the number of valence electrons, it's pretty easy. All we're going to be looking at is the s and the p orbitals, and then we're just going to count in that period. So that's 1, that's 2, that's 3, that's 4, that's 5, that's 6, that's 7.
Bless you.
Excuse me. Okay, so 7 valence electrons. Pretty simple, not too hard.
Mm-hmm.
Okay.
Simple.
Manganese has how many valence electrons? I'm sorry, not manganese, magnesium.
Oh. Magnesium. Oh, it has 2?
It has 2. Okay, so that's feeling pretty good, right? So
Mhm.
what is the importance of valence electrons? Why is it so important to us?
It tells us how many are there, or how many we need until we get to be a noble gas.
How many we need to
Or
get
how many we have. I don't know. I'm not really good at explaining, but that's how many we have, and then we need so many more to be a noble gas.
Okay. Okay. So let me see if I can try to change that up a little bit and just kind of broaden our thought on it. Okay, so valence electrons are the electrons that are going to be available to do reactions, right?
Right.
And so we're going to use these electrons to try to become stable like the noble gases, right? Okay, so for instance, we know magnesium is going to want to be like which noble gas?
Neon.
Magnesium is going to want to be like neon, right? So it can lose 2 electrons and it becomes like neon. So if magnesium loses 2 electrons, it becomes Mg plus, actually 2 plus. Because it's lost 2 electrons, that means it has more protons than it has electrons, giving it a +2 charge. Does that make sense?
Yes.
Okay. Sodium. How many valence electrons does sodium have?
Just 1.
It has 1 valence electron.
Yeah.
Okay. So if it wants to be like neon, how many electrons does it need to lose?
1.
1.
1.
So if you go sodium plus, then that guy is just like neon. Often when we draw ions, and we're saying the Lewis dot structure of those ions, we put brackets around it. And then we'll put the plus charge on the outside. Okay, so then these guys are going to be just like neon. They're going to have the same number of electrons as neon. Okay, what about, let's say, oxygen? What does oxygen need to do to be like neon?
It needs to lose, or yeah, it needs to gain 2.
it needs to gain 2 electrons.
Mhm.
So if it gains 2 electrons, well, we have 1, 2, 3, 4, 5, 6 valence electrons. Now it has 8 around it. And it's just like neon.
Mhm.
Okay. So all of these guys, because they have the same number here, they have the same number of electrons as neon. All of these guys are isoelectronic to neon. They all have the same number of electrons as neon. And so these ions, either by gaining electrons or losing electrons, become what we call isoelectronic. Okay. Okay. So this is just basically showing you that, right? Here's the Lewis dot structure of nitrogen. If we add 3 electrons, then it becomes N3. And then it becomes the same electron configuration as neon down here. You guys can't see that. Okay. Do you guys see that? Okay.
Yeah.
So same thing here with oxygen. Oxygen, if it gains 2 electrons, it becomes the same electron configuration as neon. So these guys are called isoelectronic, okay? When they have the same electron configuration, right? It doesn't have to be to a noble gas, it could be to anything. When you have the exact same number of electrons as something else, then it's considered to be isoelectronic, okay? So the thing about this also is that we have what we call monoatomic ions. Monoatomic meaning one atom ion. We're also going to have polyatomic. We'll talk about that a little bit later. Okay? Questions,
Okay.
concerns, Cash?
No, nothing.
Okay. So the same thing happens here with our positive ion, our cation. So we have sodium. Sodium loses 1. It becomes like neon. We have magnesium. It loses 2. It becomes like neon. Aluminum. It loses 3. It becomes like neon. So all of these guys can either lose or gain electrons, and they become like neon. Does that make sense?
Yes.
Good. Okay, so write the electron configuration for calcium ion with what noble gas are its ions isoelectronic to. So calcium, what is the electron configuration for calcium?
20. Is that the number? Or?
No,
That's
it's
that would be its atomic number.
Okay.
Okay, electron configuration.
for calcium. Calcium is argon.
So
and
argon would be my core.
4s2.
Okay, so it's argon, and then we come down here, 4s2, because there's 2
4s2.
electrons. Okay, so now the calcium ion. So calcium is going to want to do what?
It's gonna want to be like,
It wants to be like a noble gas, so it wants to be like argon, right?
It wants to be like argon.
Mhm.
So how can it be like argon?
it's gonna have to drop 2.
Drop 2, okay? Okay, so in the case of calcium 2+, we're losing 2 electrons, right? Because it wants to be like argon.
Right.
So if we lose 2 electrons, we're going to be getting rid of this guy. We're not going to touch the core, so it's going to be exactly the same number of electrons as argon. It's going to be that core. Make sense?
Yeah.
So let's say we have sulfur. What is the electron configuration for sulfur?
Sulfur is neon and S 3 2 or shit, hold on. S 3. Yeah, that's right, right? S 3 2.
No, how do you would you say it? You put the
Okay.
period first.
All right. Neon and then 3 S2
Okay.
and then
Is it
3 P 1 2 3 4.
4.
Okay. 3p4. Okay, so if it wants to be like argon, what does it need to do?
it needs to lose electrons, right?
Does it need to lose electrons?
No, actually it doesn't. It already
It's
it's
to
on the
gain.
same level.
It needs to gain. How many does it need to gain?
2.
2. So it'll be 2 minus. Let's see if I can move that. Can you guys see that better? 2 minus. And then in this case, if we write it out this way, it would be neon 3s2, 3p6, which would just be argon, or we could just write it as S2 argon. Okay, does that make sense?
Yeah.
Yeah.
Okay, because if we wrote argon out, say Ar, and we're going to use a noble gas that would be before argon, it would just be neon 3s2, 3p6, right? Which is the same thing as that. So it's isoelectronic, okay? Meaning the same number of electrons. Okay. Now, electrons are really, really important. They're important because they let us know how things are going to bond, what they're going to bond, right? What type of bonds they're going to form, right? So, you guys, did everybody get this down so I can erase this real quick?
Yes, I got it down.
Yeah.
Okay. So, if you think about it, there's 3 ways that you could become like a noble gas. One of the ways is if you gain electrons, right? Meaning you're going to take them from somewhere, right? The other way means that you give away electrons or you lose electrons. And then the last way would be sharing electrons, okay? Now, if you're taking and giving, that process is going to be an ionic process. That means you're gaining electrons. So we have been talking about O2. If oxygen forms a ion, how many electrons would it need to be like a noble gas? What ion is it going to form?
Wait, can you repeat that again? I'm sorry, I didn't hear you.
Let me repeat the question. I kind of messed it up. So if oxygen was going to be a noble gas, if it's trying to be a noble gas, what is going to be the ion that the oxygen is going to form? How many, is it gonna wanna gain electrons? Is it gonna wanna lose electrons? If so, how many?
It's gonna want to gain 2 to become like neon, right? Because it's closest to neons.
That is correct. So then it wants to gain 2. So then we're gonna give it its 2 electrons, right? So it'll be just like neon.
So it will
Okay.
be O2 negative.
It would be O2 negative. Okay, so if we have sodium, and if sodium wants to be like neon, what does it need to do?
It needs to lose electrons.
How many?
It can
1.
only choose 1, right?
Yep, needs to lose 1. So then it would be Na plus. Okay, now this doesn't happen in a vacuum. There's going to have to be somebody who's going to be giving, and there's going to have to be somebody who's going to be taking, right? So if I put sodium and oxygen together in a tube, then sodium is going to be giving it, and oxygen is going to be taking it. But the thing is that they're going to try to form an ionic compound that is stable, that is neutral in charge, right? What do I mean by that? What do I mean by neutral in charge? Bottom line, it has to add up to 0. So if sodium has a plus charge and oxygen has a -2 charge, how many sodiums will have to balance off that oxygen?
Would it just be 1?
So you're telling me 1 plus -2 equals 0? Is that what you're telling me?
No,
2. 2.
Sorry, it's 2.
Ah, so I need 2 of these guys. So there have to be 2 sodiums for every 1 oxygen ion, okay? So 2 sodium ions for every 1 oxygen ion. And so in this case, this is how I would write this formula in a 2O. Okay? So that means that for every 1 oxygen ion, which has a -2 charge, I have 2 sodium ions, which has a +1 charge. Does that make sense?
Yeah.
Yes.
Okay, so at the end of the day, it has to add up to 0. Okay, this guy, each sodium here has a +1, so we know it's +1. This guy is +1, this guy is +1. This oxygen is a -2, right? So it takes 2 of these guys for every 1 oxygen. 2 sodiums for every 1 oxygen. When I bring them together, they have a 0 charge. That's why we don't have any charges on these guys. Does that make sense?
Yeah.
Did you say yeah or no?
Yeah.
Okay. So let's try another one. Okay, we have aluminum and selenium. Okay, aluminum has what charge?
Does it have 3?
Okay. So it'll be aluminum,
Mm-hmm.
3 plus or 3 minus?
It'd be 3 plus, right?
That's right, because it's losing 3 electrons to be like neon. What about selenium?
Selenium would be. Would it be 6? 6 plus? Or am I
Is it going to
counting?
be 6 plus?
It's going to be gaining.
Oh yeah,
It's going to be gaining? How many?
to be negative, right? To be
2. Or
That's
1.
right.
1 or 2.
So selenium's right here. So it's going to want to be like krypton.
So it's
Right,
gonna gain.
It's going to gain 2.
Yeah.
2.
So negative.
And the reason why it gains 2 is because it's easier for it to go through and add 2 electrons rather than losing all of these electrons to be like argon. So remember, they're lazy just like us. Okay? Okay, so how can I make it so that my Al and my Se, my Al3 plus and my Se2 minus will equal 0? I want to make it so it equals 0. How many aluminum will I need and how many seleniums will I need?
2 aluminum, 3 selenium.
That is correct. So 2 aluminum and 3 selenium. Okay, so then my chemical compound would be Al2 Se3. Simple?
Yes.
Okay, it's simple math, right? Okay, now these guys form what we call an ionic bond. Ionic bonds are strong. As long as there's no water around, they're going to stay together, right? It's going to be very strong. It's going to be solids. They're really, really strong. So they're almost always solids. Okay. You guys want to try one more before we move on? And then we talk more about ionic bonds?
Yes, please.
Yes, please.
So let's do phosphorus and potassium.
Okay, so for phosphorus, it'd be -4.
-4, are you sure?
Oh wait, now you're, no wait, that right? Because I'm supposed to say 1 for gain, right?
One.
Okay, phosphorus is here. How many does it need to gain to be like a noble gas?
Only 3.
Three.
Oh,
Negative
sorry,
3.
3.
So it's going to be -3.
Yeah, and then for potassium, we're trying to lose electrons, so it's going to be a +1.
Okay, so then how many potassiums am I going to need to balance out that phosphorus?
You're going to need 2.
Just 2?
Oh, no, 3. I'm sorry, 3.
Okay.
Sorry, I'm a little off today.
All right. Okay, so then it'll be K3P. Okay. So, yes.
I know it's probably going to sound like a dumb question, but I forgot. So basically the reason why we don't have K3P3 is because we fully balance it, right, with the potassium?
That is correct.
Okay, just wanted to
Yep.
make sure because I
Yep.
got a little confused for a second.
Yeah, so always when it's totally neutral, you're never going to have a charge on anything, right? So meaning that they balance each other completely. Okay. Okay, so again, this is called ionic bonding. Okay, so now the thing about ionic bonds, right? So you have these 2 ions that are coming together. They come together because opposites attract, right? That positive attracts to that negative. And they're going to try to balance each other out completely. Always they're going to try to be neutral, right? So at the end, they shouldn't have a charge on the compound. So you should never have a charge on the compound. The biggest mistake that every student does when they try to do this, the first thing that they do is they'll say, okay, calcium is 2+ and oxygen is 2-. And then they'll leave it just like that. That would be wrong. We always want to write it as CaO, where there's no charge.
Because they balance each other out, right?
That is correct.
Mhm.
Okay. Questions, concerns, Cash? Okay. As I said earlier, most ionic compounds, almost all of them, are going to be solid at room temperature and at normal pressure because of that strong interaction, okay? That strong bonding. So these solids are going to be forming what we call a lattice. So they're going to have some type of organization. So you're going to have a positive, you're negative, you're positive, you're negative, and they're going to be alternating. I'll show you a picture of it, what it looks like a little bit later. Okay, we've talked about the charges. They have to balance out, always electronically neutral. The liquid ion compounds, and if it's in solution, they're really good at conducting electricity. Or if we heat them up enough, I mean, it takes a lot of energy to go in there to melt it. If you can actually melt it, it takes a lot of energy. But once it's melted, it'll actually conduct electricity really well because of the ions, because they're already charged. And electricity is just the electrons. So they're using those ionic components to go through that liquid, okay? And I'll show you an example of that. Okay, this is sodium metal mixed in with chlorine gas. Now this is a very volatile reaction. It's kind of violent, right? So it's like it ignites and everything. It gets nice and glowy and pretty fast. Now, it kind of makes sense because we know that sodium is really anxious to be a noble gas. And chlorine is really anxious to be a noble gas because sodium is only one away, right? If it loses one electron, it becomes a noble gas. Chlorine is one away and it becomes a noble gas. So when you get two guys that are really anxious together, guess what's going to happen? Whoosh, right?
Mm-hmm.
Very violent reaction, right?
Right.
So let me show you what happens.
Fireworks.
Sodium is going to lose that electron. Chlorine is going to gain it, right? So as soon as sodium drops it, chlorine got it. And it works to both of their favor. And then as soon as that happens, they become positive and negative, and then they come together. Do you guys put salt on your food?
Yeah.
All right. Do you blow up when you eat salt?
Yeah. Mm-hmm.
You do?
I do. Well, I get bloated.
You
Salt
get
water.
bloated, but you don't blow up, right?
Oh no, I don't.
Do you yellow smoke and stuff and flames come out of your mouth and stuff like that?
No.
No, it doesn't, right?
You-
Because
you
they
retain water.
neutralize each other, right?
Right.
They stabilize each other. What was that, Diana?
You retain water.
You retain water. Yes, but that's for different reasons, right? So, but you don't blow up, do you? You're like, I don't see any of you guys blowing flames or anything, right?
Mm-mm.
So you don't have that violent reaction because those ions are now neutral. They're like those noble gases. They're stable. They're not going to want to react, right? Because they're happy with each other. And so it just adds flavor to our food, right? Or helps us get out of ice, you know?
Both, yeah.
Okay. So if you take a look here, so remember I told you there will be a figure showing you that?
Yeah.
So
Lattice.
lattice. Yeah. So here we have the gray spheres are sodium. The green spheres are chlorine. So this is our sodium ion. This is our chloride ion. So they're alternating between each other. Have you noticed?
Mm-hmm.
And it's both up and down. So really, because the whole thing is positive, it's going to attract things that are negative around it. And they're going to orient themselves so they're alternating, you know, almost evenly. And that's what's kind of holding them together, right? Is those charges, okay? So here's another picture of it shown two different ways, okay? So you guys, you kind of see that, right? Makes sense?
Yeah.
Okay, so I said it conducts electricity. So when we melt these ions, if we get them high enough that they're in a liquid state, or if we put them in water where water will actually dissociate the ionic components, right? Then those ions are free to move, right? So then you have plus and minus charges in solution that will be able to interact with the electricity or the electrons that are passing through that, through the electrode, right? Because electricity is just electrons moving through metal, right? Being passed on through that metal, okay? Make sense?
Yeah.
Okay, so that's ionic bond. So let's talk about covalent bond. Covalent bonding is sharing. How many of you guys have siblings?
I do.
Right?
I do.
So did you guys have to share stuff?
Supposed to.
You're supposed to, right? Okay, that's good. That's good to know that I'm not the only one like that. Okay, so in that concept, we know what sharing means, right? So in this context, they're sharing electrons. They're sharing electrons so that they can be like a noble gas. So if we think about it, we want to try to get, if we paid attention to all of the things, we want to try to get 8 electrons around us. So we want to obey what we call the octet rule. The octet rule means that you have 8 electrons surrounding you, right? So we had talked about oxygen. If it lost 2 electrons, if it gains 2 electrons, it would have 8 electrons around it, just like neon.
Yeah.
Right? Okay, so here we're going to be doing a little bit different. They're not going to be taking electrons for themselves only. They're going to have to share it with them. Okay, so we're going to start off here with hydrogen. Hydrogen is a special case. Hydrogen has 1 valence electron.
Yeah.
So each hydrogen has 1 valence electron. They want to be like who?
Helium.
Helium. And how many electrons does helium have around it?
2.
It has 2. So hydrogen, at most, will only have 2 electrons around it. So because it wants to be just like helium. So this works out great. So if you have 2 hydrogen molecules together, these electrons are going to be shared. So we draw a line between the 2, meaning that they're sharing. Each one of them are providing electrons that they're sharing. Okay? Okay, and you guys can kind of see this down here. Okay? So we use the line to represent a bond. So this is called a covalent bond, where the electrons are being shared between those 2 atoms. Okay, are you with me?
Yeah.
Okay, so if we have oxygen, how many valence electrons does oxygen have?
8
8, are you sure?
5.
valence electrons.
Valence electrons.
Oh, 6.
Would it have 6?
It has 6 valence electrons, right? So
Yeah.
always remember, go in that period where it's at, and then just count the S and the P until you get to that element, right? So oxygen has 6 valence electrons. So I want to fix it so that both of these oxygens have 8 around it. So we need to find a way that they're sharing electrons so that both have 8 around it. So if I go 1, 2, 3, 4, I'll put 1 in the middle. 1, 2, 3, 4, 1, 2. So we have a total of 12 electrons to work with. So that's 2, 4, 6, 8, 10, 12. So does this guy have 8 around it? The first oxygen?
4.
Right here.
No.
I see 6.
No.
It only has
You only have
6.
6.
So I need to do something more, right?
Yeah.
So how about I do this? And I drag these guys and I put those in the middle too. So in this case, I have
2,
1, 2,
4.
1, 2, and I have 4 electrons that I'm sharing.
8, 6.
So if we count that, 2,
Yeah.
4, 6, 8 around this oxygen, 2, 4, 6, 8 around this oxygen, and
Yeah.
let me count, I need to have a total of 12, 2, 4, 6, 8, 10, 12. Okay, that works out. So it's going to look something like this.
Share the 4. Okay.
So we're sharing 4 electrons. So we make what we call a double bond, right? One line represents the sharing of 2 electrons. 2 lines or a double bond representing sharing of 4 electrons. Okay, does that make sense?
Yes.
Yeah.
Okay. Okay, let's do this guy. Nitrogen. So how many valence electrons does nitrogen have around?
5.
5.
5. Okay, so I want you guys to help me out with this one. How many electrons do we need to share?
Three.
3 electrons? Each
Five.
nitrogen?
No, we
What
know.
are you trying? What are we
Ten.
trying to be like helium?
No, we're not trying to be like helium. We're trying to be like neon. We
Oh,
want 8 around us.
Oh.
3.
3.
So we're going to be sharing 3 electrons each? Is that what you're telling me? Or
No,
just 3 electrons?
we're
No, 3 electrons.
So 6. 6.
Okay, wait.
Electrons each.
So we're going to be
3.
sharing. Okay, so altogether, we know that there's 10 electrons that we're working.
yes, correct. There's 10.
So you're telling me I need to put 3 in the middle. Is that what you're saying?
Yes.
Okay, 3 in the middle on both sides. So that's a triple bond.
Triple bond. 6
Okay.
electrons.
So it's a
Didn't I
total
say
of 6.
3?
What was that?
Didn't I say 3 earlier?
You said 3 electrons, but does that mean you're sharing 3 electrons, or are you?
Oh, okay. I thought
You
I
know
was
what
tripping.
I'm
for a
saying?
minute. Yeah.
Okay, so triple bond. So that's 2, 4, 6, 8, 10 total. 10 total electrons. And then that's 2, 4, 6, 8 around this end. That's 2, 4, 6, 8 around that end.
Yeah.
Okay, simple, not too hard.
What's the highest it can go to as like triple?
A triple bond is the only one that is stable enough to exist.
Okay.
Technically, it can form carbon, which has 4 electrons, valence electrons. Technically, it can do that, but it's not stable enough because of the structure. But this is not a stable structure.
Okay.
Okay, so now covalent bonded compounds, right? Or covalent compounds. So these guys, they're not going to be able to conduct electricity. Okay, so here we have water, H2O. And let me give you a hint. Any time that you have, or most cases, where you have non-metals together, they're going to form a covalent bond in most cases, okay? The water forms a covalent bond, right? So let's draw the Lewis dot structure for water. So we know that hydrogen can never, ever, ever, ever be in the middle. Let me repeat that. Hydrogen can never, ever be in the middle because hydrogen can only form 1 bond with something. It can't form 2 bonds, okay? So
That's
hydrogen
equal.
can never be in the middle. What was that?
That's an equal, right? Those are like non-polar something.
Yeah, this guy would be a non-polar covalent bond. I mean, this guy would be a polar covalent bond. Polar covalent bond.
Polar covalent bond, yes. It is.
Yeah, we'll talk about that here in a second. I'm building up to it. You've been reading.
I've been watching videos.
That's good. Okay, so oxygen is going to be in the middle. How many valence electrons does oxygen have?
6.
Okay, and then hydrogen has how many?
1
1.
times 2.
Okay. Oops, I got carried away. Okay. Okay, so we're going to be sharing that 1 bond. So hydrogen has 2 electrons around it. Hydrogen has 2 electrons around it. And the oxygen has how many around it?
4.
It has 4. It has 4?
No, it doesn't.
Oh, I know. I have 4, 5, 6, 7, 8.
8. Okay. It has 8 around it. Okay. So we have 8. So we reached that octet. So we're in good shape, right? So these guys, because they're sharing the electrons, there's no electrons free to sit there and carry the charges. There's no positive and negative ions that exist. So you're not going to get electricity flowing through it. Okay, does that make sense?
Yeah.
Yeah.
Now, if we put salt in there, we put salt in our water, which is what happens here. We have water and salt. So salt is going to break up into its ionic components. So it's going to have Na plus and the Cl minus, Na plus, Cl minus. And so these guys are going to be able to, oops. It's going to be able to sit there and carry the electrons, right? That are flowing through the electricity. Okay, so sucrose. Sucrose is just sugar. Its chemical formula is C12H22O11. Okay, all nonmetals. What type of bond is it going to form?
Covalent.
Going to form a covalent bond. Again, since it's covalent, it's not going to be able to conduct electricity. Okay, did you guys see the difference between covalent bonds and ionic bonds?
Mm-hmm.
Ionic is based upon charges, plus and minuses. Covalent is where you're sharing electrons.
Mm-hmm.
Okay. Okay, so here, the thing about those sharing of electrons, what they really are, you're going to have this overlap, an overlap between the electron density, or the charge density is what they call it. Okay, so you just have these clouds of electrons that are circling the nucleus and stuff like that. They're actually going to overlap with each other when electrons are being shared. So it's going to look something like this. Okay, here are two hydrogens, right? So you have the electron circling the nucleus, the electron circling the nucleus, but when they come together, they form this cloud around both of them, and they have overlap between two clouds. Do you see that? So these guys are just sharing in that regard.
Mm-hmm.
Okay? Okay, so if I have fluorine, we know that fluorine is a diatomic molecule, F2. So what is the electron configuration for that going to look like?
Helium. 2s2.
I'm sorry, not the electron configuration. What is the Lewis dot structure going to look like? My bad.
6, 7.
Right?
What was that? So how many valence electrons does fluorine have?
7.
7.
7.
7. Okay. 1, 2, 3, 4, 5, 6, 7. This guy's gonna have 1, 2, 3, 4, 5, 6, 7. Okay. So how can I make it so that they have 8 around both of them?
Single bond.
Single bond. Okay, simple.
Yeah.
So they always have to have 8 surrounding them.
That is a very good question. So in most cases, we're going to try to have 8 around us. There are going to be exceptions.
Hydrogen is water.
What was that?
Hydrogen an exception.
Yes, hydrogen is an exception, but it's going to try to be like the noble gas helium. That's the reason why it's an exception.
Mm-hmm.
There are going to be other exceptions that we're going to talk about later, but we're going to build up to it. So I just want you to get in the habit of doing this first, right? Okay, so are you guys ready to give this a shot? Okay. So we're going to go. Let's see. There was something else I forgot. 1, 2, 3, 4. Oh, yeah. And okay, so I'm going to do this one for you real quick. So I want to show you something. So I'm going to show you two ways of kind of remembering what goes in the center. So sometimes we have more than two things reacting, two elements in it, right? So carbon dioxide has 3, right? It has 2 hydrogens and 1 carbon. So we need to figure out who's going to go in the middle.
2
Now,
oxygens.
Carbon will be in the middle, right? And then two
It would be carbon.
It would
Yes.
be carbon. Carbon's a whore.
Yes, carbon's
Yeah.
a whore, exactly.
Carbon's a whore.
Carbon is going to be in the middle. Okay, so that's one way of remembering it. So I guess I have 3 ways of remembering it. The third way of remembering it is the further away you are from being a noble gas, the more likely you're going to be in the middle. Okay, so nitrogen is further away than oxygen. So if we have a couple of oxygens and nitrogen, then we know that that nitrogen is going to be in the middle. Okay, if we have carbon and nitrogen, carbon's going to be in the middle. If we have fluorine and oxygen, oxygen is going to be in the middle. Okay.
Okay.
Okay, so now that we've talked about that, let's go ahead and go back to what we're doing. Okay, so did you guys get this written down?
No. No.
Yeah.
Yes.
Okay.
Okay, so I'm going to put you guys in groups for about 10 minutes, and I want you guys to work on it together to draw the Lewis structures for all of this. Okay?
Dr. Henry, before you put us in groups, is there any way you can, like once you're done with lecture and stuff, show us how to work the on our Chem 101? You know how we have to draw the Lewis structure?
Yep, I can show you that.
It's a little confusing how to use that program. Like I'm stuck on
Okay,
it.
okay, we can do it.
Okay, thanks.
Okay, so let me put you guys in groups. You guys have to help me here. So we have CO. How many valence electrons does carbon have?
4.
4,
4.
4.
Okay, so, and then oxygen has how many?
6.
6.
Okay, so we have a total of 10 electrons that we're working with.
Oh.
Now, you guys all know that you have 10 electrons you're working with. You can't end up having 20 electrons around each atom, right? Because you're only working with 10. So you have to make sure that you only use those 10. Okay? So what can I do to make this work? I want it so that there's 8 around both atoms.
Yeah.
So
So what am I going to do?
You're gonna move 2 electrons. To the,
So I'm going to move 2 electrons.
No
Is
oxygen.
that what I want to do?
No.
No.
Okay. So I'll move these 2 electrons,
Actually,
and
no.
that's it?
No. We want to do a bond.
A triple bond.
A triple bond. Also, I'm going to move these 2 sets of electrons towards the middle. So then I'll have or like that.
And then put, yeah.
Okay, so let's count it. 2, 4, 6, 8, 10. That's 10 electrons. So that's 2, 4, 6, 8 around the carbon, 2, 4, 6, 8 around the oxygen. Everybody got that?
Yeah.
Good,
I was
bad, or
way
indifferent?
off. I was off on mine.
Yeah. Do the triple bond.
Okay, so what about the CO2?
Carbon in the middle.
Carbon in the middle, and it has
2 oxygens on each side. Yeah. And then oxygen has 6 valence.
okay.
can use those two bonds in between, like those valence in between carbon to join them, right?
Okay, so you're saying I'm doing this.
Oh, you're gonna do a double bond.
Ah, I'm gonna do a double bond because I would only have 4 around carbon.
Yeah.
Oh, okay. So then I need to take 2 from here.
Does it matter where we take it from, or it does? No?
It doesn't really matter. Because they're all moving anyway, right? So, okay, so that's it.
Yeah.
How many total
Yes.
electrons should we have? We had 6
10.
times 2 plus 4. Is that 16?
Yeah.
So 2, 4, 6, 8, 10, 12, 14, 16. Okay, works out. So we also had this guy.
So that one would be N in the middle,
Okay,
and then you're gonna have 3 hydrogens spread out.
okay,
And then after you put the hydrogens, you're gonna have 2 of the 2 valence electrons on top of the nitrogen.
okay. So we know that nitrogen has 5 valence electrons
Mhm.
and hydrogen has 3 altogether, 1 in each one. So that's a total of 8 that we're working with.
Mhm.
So that's 2, 4, 6, 8. Works out perfectly.
Yes.
Everybody's happy. Okay, our last one was CH4.
No, we actually
Oh,
have another one.
we have one more. I know. We forgot the sulfur.
Each
So
one
this-
is like a cross, basically. Carbon's gonna be in the middle, and we're gonna have 4 hydrogen around it.
Okay, and
Hydrogen has
okay, so
1.
who's going to be in the middle in this case?
Sulfur. And we're gonna have 2.
Sulfur?
So sulfur has 6.
We're gonna do a bond for each hydrogen, right?
Okay,
2 connected.
okay, that's it. That's 2, 4, 6, 8 around sulfur, 2 around hydrogen, 2 around hydrogen. We're good to go. Simple.
Yeah.
Somewhat.
So let's talk about your homework. Since Daisy brought that up. Well, actually, let me go over one more slide. So when we were talking about our Lewis structure, these electrons that aren't involved in bonding, these are called your lone pair, right? And so we want to keep track of those too. We want to make sure that we know what's going on in that situation. And so we also know that they also they're counted towards that octet rule. You guys are familiar with the octet rule, right? Questions? Concerns?
No.
Okay. So question number 22, draw Lewis structure of ammonia.
Ammonia.
Okay. Click on the area to draw.
Did you get to see that way?
So the atom that you click on, if you double click on it, it takes you to the periodic table. You can say what it is. It's our center atom is going to be who? For ammonia.
Ammonia.
Oh, I see. Okay.
Okay. So that's going to be our center atom. We're also going to add a bond to it, right? And we're going to add another bond to it. So there are 3 bonds. That's for the 3 hydrogens, right?
Right.
Okay.
So we'll
So-
click off the other ones and put hydrogen, or?
Yep, we'll click on the other ones and put hydrogen. So if I want to add electrons, I just move this guy where it says electron, and then I click on hydrogen. Then I click on that one. Okay. So one day, actually, I can do it with you guys. I'll do it with you guys early. This is called the formal charge. The formal charge is, it'll help you realize, because there's certain times that we're going to have options to the electron configure, the Lewis dot structure for the compound. So sometimes we're going to have options of the ones that we can pick. So you always want to try to find the one that has the formal charges that is closest to 0, right? And if you notice, it'll be on every atom, okay? The way you calculate your formal charge is, it is formal charge is going to equal the valence electrons of that atom minus the number of lone pair electrons minus the number of bonds. Okay, so the formal charge on this hydrogen here, this one right here. So how many valence electrons does it have? Anyone?
One.
One.
Sorry, I was on mute.
Okay, hydrogen has 1 valence electron. Are there any lone pairs around hydrogen?
Mm,
No.
helium, but
Lone pair would be electrons like this. Are there any lone pairs around hydrogen?
No.
oh no.
No. How many bonds between?
1.
Okay, so we add that up together, it equals 0. And you want to try to get it as close to 0 as possible. Sometimes you can't get it to 0, but you want it to be as close to 0 as possible. Okay, what about the nitrogen? All of the hydrogens are going to be the same.
Lone pair.
How many valence electrons?
Oh,
5.
yeah.
5.
5 valence electrons. How many lone pair electrons?
1.
3.
Lone pair electrons. How many
3.
electrons do you see up here?
2.
Oh,
Oh,
Okay.
2. Oh, the lone pair is the dot?
Yes, those are lone pairs. So
But isn't-
this guy is a lone pair, but there are 2 lone pair electrons.
Isn't a pair 1?
No, a pair is 2, right? But we're saying lone pair electrons. There are 2 electrons to make up a lone pair.
Right. 2
Like
electrons.
you have a pair of shoes, right?
Yeah, that's 1 pair.
Yes, it's 1 pair, but that's why I say lone pair electrons. How many lone pair electrons do we have?
1 pair of 2 electrons.
No, I'm not saying a pair of electrons, right? I'm saying lone pair. Lone pair is 2, but there are 2 electrons, right?
Right.
It's the number of electrons in that lone pair. There could be multiple lone pairs. I could have 5 lone pairs around something. I'll show you an example here in a second.
Okay.
Okay, not to a 5. So it's 2 electrons. So you want to count each electron that is around it. Okay. And then the number of bonds. How many bonds?
3.
3 bonds. So we add that together. That equals 0. Okay. So that's why you have a formal charge of 0, 0, 0, 0. This guy actually calculates. Does that make sense?
Yeah.
You guys have that look. It makes me worried.
My
Do
phone's
another
about
one,
to-
Dr. Henry.
What was that?
Can you do another one?
Yes, I can. So let me find one where we talk about That's the octet rule. Yeah, actually, this will work out.
Oh,
Okay. So we want to fix this so this guy obeys the octet rule. So they kind of started our structure for us, right? So xenon is a noble gas. Now, sometimes noble gases can be pumped into doing what they want, to what other things want, especially if they're low on the periodic table. So xenon is pretty low on the periodic table, so it will often get pumped by oxygen or chlorine and stuff like that, okay? So here's xenon. How many valence electrons does xenon have?
Xenon or something. Xenon has
8.
Have
two,
eight.
three, 4, 5.
It has 8 valence electrons, right?
1, 2, 3.
Noble gas, it has 8 around it. Okay, so xenon has 8. Oxygen has how many?
6.
And we have 3 of those, so times 3. So that's 18.
18.
18 plus 8.
26.
26.
So we have 26 electrons that we're working with. Okay, so let's start putting some electrons here. Sorry. So I'm going to click on xenon. I know I have some extra electrons to work with, right? I know I have at least 2 there, right? So this oxygen, for it to have a complete octet, we need how many electrons around?
6.
8.
6, and then that's 8.
Yeah.
Okay.
Oh.
Oh, that's why you move it.
Okay, so then let's see, that's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Make sure I count it right. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Okay, so that's all 26, right?
Yes.
Is there 8 electrons around here?
Yeah.
Yeah.
8 electron around here?
Yes.
8 electrons around here?
Mm.
Yes.
8 electrons around here.
Yes.
Okay, so if we wanted to check the formal charges. All right, so xenon, how many valence electrons does it have?
8.
8.
We have 8. How many lone pair electrons?
2.
And then how many bonds?
3.
3.
This guy is horrible right now, right? It has what, a plus? That would be a +3. That is a horrible charge. Okay, so each of the oxygens. Valence electrons?
6.
6.
6. Lone pair electrons?
1.
1.
Lone pair electrons?
Oh,
Oh.
2, 4, 6.
6. And bonds?
1.
Just 1.
Okay, so then that's a -1. And so each of those, each oxygen is going to have a -1.
Okay.
So in reality, even though it obeys the octet rule, the one that obeys the octet rule is horrible in terms of structure because that has a +3 charge. It's pretty far away from 0. So the chances of it maintaining this structure is not likely. Okay, but that's what they're asking you.
Okay.
Okay,
Mm-hmm.
simple, not too hard.
Kind of. It's okay.
It's okay. Good. Want to do one more for the road? And then we'll go to the lab and do some more.
I have all the way through. I did 33, but I think I got 2 wrong.
33?
Yes.
Okay. So determine the number of valence electrons in dimethyl ethyl, and they give you the chemical formula, and then draw the corresponding Lewis structure. Okay, dimethyl ethyl. So the way that they have this drawn, they're letting you know that you have a C here. It's going to be attached to an O, and then another C over here. And then these guys are all going to be attached together to hydrogens. So how many more valence electrons do I need? I mean, how many to make oxygen reach its octet?
4.
4.
Okay, so if I count the total number of valence electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Make sure I count it right. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So there's a total of 20 valence electrons. So how would I draw that structure? Okay, so I'm going to put my oxygen here. It's going to have a bond. You know, that's going to be a carbon. And this one's going to be a carbon. This oxygen is going to have and this carbon is going to have, oops, went too far. 3 bonds, 4 bonds. Hydrogen, hydrogen, hydrogen. God, this guy's responding so much better than it did before. You used to have to wait a minute before you.
It would reflect what you clicked on.
Yeah, it's gotten so much better.
Maybe no one's doing their homework right now.
Maybe that's what it is. Yeah. Everybody's on spring break. Pretty simple, right? Not too hard.
Yeah.
So a couple of really quick things to remember. Best thing to always do is count how many valence electrons that you're going to be working with. And at the end, make sure that that's how many electrons that you used. Then make sure that everybody has 8 around them, unless they're not supposed to have 8, like hydrogen. All right. Okay. Okay.